In this module, we will focus on vibrational partition function and on calculation of the properties using this vibrational partition function. As you know, we have been working on gaseous systems, and if a gaseous molecule is diatomic, it will have 3 translational degrees of freedom, 2 rotational and 1 vibrational. And if we generalize it, we know that if there are n atoms in a molecule, then in total there will be 3 n degrees of freedom, and if the polyatomic molecule is linear, then it will have 3 translational, 2 rotational and 3 n minus 5 vibrational degrees of freedom. On the other hand, if this polyatomic molecule is nonlinear, it will have 3 translational, 3 rotational and 3 n minus 6 vibrational degrees of freedom. In our calculations and in our studies, we have been focusing on diatomic gaseous molecule, that means n is 2, and therefore, it will have only 1 vibrational degree of freedom. We also know that for a polyatomic molecule, the total partition function has the contributions from translational, rotational and vibrational degrees of freedom. That means, small q, that is the partition function of a polyatomic molecule, is the product of qt, which is the translational, qr rotational and qv, which is the vibrational partition function. And we have also studied that if we have n polyatomic molecules, or in our present study, if we have n diatomic gaseous molecules, then there is a macroscopic partition function which we denote by capital Q, and that Q, capital Q, is equal to small q raised to the power n upon n factorial. And Q, since it is Qt, Qr, Qv, then this expression, as it has been shown here in equation 1, it becomes Qt, Qr, Qv raised to the power n divided by n factorial. And once we have the values of Qt, Qr and Qv, using that we can calculate the various properties. We have already derived in our earlier modules that the total energy can also be calculated, and it will have expressions as it is shown in equation 2. You can see the first term on the right hand side of equation 2 is translational contribution to the energy. Second term is rotational contribution to the energy, and third is the vibrational contribution to the energies. The first two contributions, translational and rotational, we have already calculated in our earlier modules. In today's module, we will focus on QV and then also calculate the vibrational contribution to energy. Similarly, if you look at equation 3, here is the expression for entropy, and you see the first term on the right hand side, which is in the parenthesis consisting of two parts. This is nothing else but the translational contribution to entropy. And if you recall, this equation or these two terms taken together also constitute what we derived as Seku-Tetrode equation. Then the next two terms which are in the parenthesis, they are giving us rotational contribution to entropy, and these we calculated in our last module. And the next two terms are the vibrational contribution to entropy, which we will calculate in this module today. Now, in order to proceed further, you will all agree that first we need to know what is vibrational contribution or what is the vibrational partition function of a diatomic gaseous molecule. In order to calculate the vibrational partition function of a diatomic molecule, we need to know what are the various vibrational energy levels, and these vibrational energy levels can be calculated using quantum mechanical results. You must have studied in quantum mechanics a case of linear harmonic oscillator. There we solve Schrodinger equation for a linear harmonic oscillator and then calculate the corresponding wave function and the vibrational energy. We will very quickly recall all those things. You know that a linear harmonic oscillator, the vibrations are simple harmonic, and that means they are obeying Hooke's law. Hooke's law means that the restoring force and the displacement, they are in opposite directions, as you can see in this equation 4. F res is equal to minus kf x, where kf is the force constant and x is the displacement, and negative sign indicates that these two are in the opposite direction. Using this restoring force, one can calculate the potential energy of a linear harmonic oscillator, and this potential energy is given by the relation, as you can see here, V is equal to half kf x square. I am sure you must have read this equation earlier, and this variation of potential energy with displacement x is shown in the diagram, as you can see here. Now, once we have the potential energy for a linear harmonic oscillator, one can write down the Schrodinger equation for a linear harmonic oscillator which is undergoing vibrations along x direction. And as you can see in equation 6, we have the Schrodinger equation for a linear harmonic oscillator having potential energy is equal to half kf x square. We have minus h square upon 8 pi square mu. Mu is the reduced mass of a harmonic oscillator. d2 by dx2, we are taking x because we are assuming vibrations to be along x direction, then plus half kf x square, which is the potential energy, then psi v, which is the vibrational wave function, is equal to ev psi v. This is the Schrodinger equation, time independent Schrodinger equation for a linear harmonic oscillator. If one solves this equation, you know we get two things. One is vibrational wave function psi v, which is given by the expression as shown in equation 7. Psi v is equal to n v h v y e to the power minus y square by 2. This is a well known expression for the vibrational wave function, and here the various terms have their own meanings, which are already shown. N v refers to the normalization constant and h v y refers to the Hermite polynomial, and other symbols are shown there. Besides vibrational wave function, solving Schrodinger equation also gives you vibrational energy, which is as shown in equation 8. It is E v is equal to h nu v plus half. Here v is the vibrational quantum number, which can have values from 0, 1, 2, 3 onwards, and nu is the vibrational frequency. This vibrational frequency for a linear harmonic oscillator is given by the equation as shown in equation 9. Nu is equal to 1 by 2 pi under root kf by mu, where kf, as you know, is the force constant and mu is the reduced mass, which is given by the expression mu is equal to m1 m2 upon m1 plus m2. In the case of a diatomic gaseous molecules, m1 and m2 will be the respective masses of the two atoms which are constituting the diatomic molecule. One thing which you should notice from this vibrational energy expression is that when V is 0, the energy becomes half h nu V, that is called 0 point energy. That means the lowest energy which a linear harmonic oscillator possesses is not 0, but 0 point energy. This is a very important thing which you should keep it in mind, because we will be using it later on. We can also see here in these two diagrams the plots of the vibrational wave function and also the plots of the corresponding square of the wave function, which is the corresponding probability density. So, these two plots are shown here, and they are for each vibrational quantum number V0, V1, 2, etc. and both these plots show how the wave function and how the probability density varies as a function of x. Once we have solved Schrodinger equation for a linear harmonic oscillator and have obtained vibrational partition function and the vibrational energy, now using this vibrational energy expression which we got in equation 8, one can calculate the corresponding vibrational partition function. Vibrational partition function, as it is shown in equation 10, is given by the expression QV is equal to summation GV e to the power minus EV upon KB by T, where KB is the Boltzmann constant. Now, in the case of linear harmonic oscillator for a diatomic gaseous molecule, degeneracy is 1. Therefore, here we would be carrying out summation over all allowed vibrational energy levels, assuming degeneracy to be the 1, and therefore, the expression for QV will become, as you can see here, it is shown in equation 12, keeping degeneracy to be 1. And now, if we expand it, as you see in equation 13, QV is equal to e to the power minus h nu upon 2 kBt plus e to the power minus 3 by 2 h nu upon kBt, then e to the power minus 5 by 2 h nu upon kB by T. This is what we are getting is by putting V is equal to 0, V is equal to 1, etc. These are the various terms which are coming in the summation. And please notice that all vibrational energy levels are equally spaced. Now, if we take e to the power minus h nu upon 2 kBt to be the common, then we have equation as it is shown in equation 14. And if we further simplify it and solve it, you will notice that QV comes to be e to the power minus h nu upon 2 kBt into 1 upon 1 minus e to the power minus h nu upon kBt, as it is shown in equation 15. And if this is rearranged, we ultimately get the expression for vibrational partition function, which is shown in equation 16. It is shown that QV, that means the vibrational partition function for a diatomic gaseous molecule is equal to e to the power minus h nu upon 2 kBt divided by 1 minus e to the power minus h nu upon kBt. So, this is the expression for the vibrational partition function. You know, in this expression, if you look at this equation 16, the term h nu upon kB, this will have the units of temperature, and therefore, we replace it by theta v and call it vibrational temperature. So, theta v is h nu upon kB, as it is written in equation 17, and if we substitute it back in equation 16, we get the corresponding new form of vibrational partition function, which comes out to be qv is equal to e to the power minus theta v by 2 t divided by 1 minus e to the power minus theta v by t, as it is shown in equation 20. So, this is the expression for vibrational partition function. A further light on vibrational temperature, please notice that vibrational temperature is theta v is equal to h nu upon k b. It can be further written as h upon, if we substitute the value of nu, which is 1 upon 2 pi kf upon mu under root, then we have in equation 18, and then if we simplify, we have in equation 9 the expression for the force constant in terms of vibrational temperature. That means, as you can see here, kf is equal to 4 pi square theta v square kb square mu upon h square. This is the expression for force constant in terms of vibrational temperature. Now, after having calculated the vibrational partition function, we will go to the calculation of the thermodynamic properties using this vibrational partition function. And the first property which we will calculate, as we mentioned earlier also, that is the energy. We are assuming, please remember that the bulk system of the particles is obeying Maxwell-Boltzmann statistics. And we also know, as we showed it, that the vibrational contribution to energy is given as shown in equation 21, that is kb t square delta ln qv raised to the power n divided by delta t. Now, in this expression, we will substitute the value of vibrational partition function, and once we substitute it, you can see here, and if we simplify it, see we have substituted the values and then in equation 23, and then if this expression is simplified, we find that ultimately the energy of diatomic gaseous molecule will have its vibrational contribution as it is shown in equation 27. E v is equal to n k b theta v by 2 plus n k b theta v e to the power minus theta v by t divided by 1 minus e to the power minus theta v by t. So, this is the vibrational contribution to energy. But please remember that here n is the total number of diatomic gaseous molecules in the system. Now, if this n is Avogadro's number, then n can be replaced by n a and then n a k b, that means Avogadro number multiplied by Boltzmann constant will give us the gas constant, and then we will have the final equation for energy, which will be, as you can see here, is given in equation 29. E v is equal to r theta v by 2, r is coming because it is per mole now, r theta v by 2 plus r theta v e to the power minus theta v by t, then divided by 1 minus e to the power minus theta v by t. So, this is the vibrational contribution to energy. One thing which you notice here, that this vibrational contribution to energy has two terms. The first term is independent of temperature, but the second term depends upon temperature. And what will be the two extremes? We will consider them. Case 1 will be the case when temperature is very, very large, and very large in comparison to vibrational temperature. That means, T is much greater than theta v, or in other words, theta v by T is very small. So, making use of this, we will look at this equation and simplify it. As you can see here, that we have on simplification e to the power theta v by t, we have brought it in the denominator and then we are solving it, and you can see that it becomes E v is equal to r theta v by 2 plus r theta v, and then we have e to the power theta v by t minus 1, because we are taking that term inside the parenthesis. And then since theta v by t is very small, then we know very well that if x is very small, e to the power x can be written by this expression 1 plus x square. So, making that substitution here, and if we simplify it, as you see in equations 33 and 34, ultimately on simplification we get E v is equal to r theta v by 2 plus r t. That is the case when temperature is very high. This is the contribution, vibrational contribution to energy. On the other hand, if we take a second possibility that temperature is very low as compared to vibrational temperature, then you can notice that theta v by t will become very large. And again, if we start from equation 31 and simplify it, so using the condition that theta v by t is very large, we get a new energy expression which is the vibrational contribution to energy, and that is as it is shown in equation 36. It is r theta v by 2 plus r theta v divided by e to the power theta v by t. But please notice here that the first term on the right hand side of equation 36 is the 0 point energy, that is r theta v by 2 is corresponding to 0 point energy for 1 mole, because we are assuming here that we are taking 1 mole of the corresponding gaseous system. That means capital N is equal to N A. After having studied the vibrational contribution of energy, now we will focus on the vibrational contribution of entropy. And as we have already learned, as it is shown in equation 39, that the vibrational contribution to entropy is given by the expression S v is equal to k b ln q v raised to the power n plus E v by t. Now, we substitute the value of q v from equation what we have already derived 20, and then if we substitute, then we have S v is equal to n k b ln e to the power minus theta v by 2 t divided by 1 minus e to the power minus theta v by t plus E v by t as shown in equation 40. For 1 mole of the gaseous molecules, that means n is equal to N A, we make further substitution and then simplify it, and we notice that what we get is the total entropy, that means the vibrational contribution of entropy is r theta v divided by e to the power theta v by t minus 1 minus r ln 1 minus e to the power minus theta v by t. So, that is the vibrational contribution of entropy. So, we have calculated using vibrational partition function two thermodynamic properties E and S, that is the entropy. And as we have already in our earlier modules derived expressions for other thermodynamic properties, one can similarly calculate other thermodynamic properties like Gibbs free energy, enthalpy, etc. So, in this module today, we have focused on the calculation of the vibrational partition function of a diatomic gaseous molecule. For a diatomic gaseous molecule, there is only one vibrational degree of freedom, and for this molecule we have calculated the vibrational partition function. For calculating the vibrational partition function, one needs vibrational energy, which we got from the corresponding quantum mechanical results. For a linear harmonic oscillator, we wrote Schrodinger equation for a diatomic gaseous molecule, and then solved it. We showed that the solution of this gives us vibrational wave function and the energy which comes out to be, here V is the vibrational quantum number and it can have values 0, 1, 2 etc. And nu is the frequency which is given by the expression nu is equal to 1 upon 2 pi kF upon mu. Using this energy expression, we calculated vibrational partition function which comes out to be qV is equal to e to the power minus h nu upon 2 kBt divided by 1 minus e to the power minus h nu upon kBt. Here is the expression, and then we also substituted for h nu upon kb the corresponding expression as theta v, and we called it as a vibrational temperature. Then using this vibrational partition function, we calculated the thermodynamic properties, we calculated the vibrational contribution to energy, and this came out to be E v is equal to r theta v by 2 plus r theta v upon e to the power theta v by t minus 1. For this vibrational contribution to energy, we studied two cases when the temperature is very high, and also we studied in detail the case when temperature is very low. Both these high and low were in comparison to vibrational temperatures. And after that, we calculated the expression for the vibrational contribution to entropy, and we showed that SV, which is the vibrational contribution to entropy, comes to be equal to r theta v upon e to the power theta v by t minus 1 into t minus r ln into 1 minus e to the power minus theta v by t. So, that is basically what we have done in this module. We will continue with our discussion on some further new aspects of vibrational partition function in our next module.